So let's go ahead and get started. As Kim mentioned, today's topic is going to be comparison of fatigue analysis methods. And we're going to be following that up at the end with a small demonstration in nCode 8 so that some of you guys who are a little less familiar with the interface can get an idea of what that looks like. Before we begin, though, I just want to review the 3 software products that we have at nCode. And those are, starting on the left, GlyphWorks, which is a tool that is intended mostly for test engineers. It's going to allow them to take measured data, which can be in all sorts of forms. It could be strain gauge data, accelerometer data, process that data, come up with some results, maybe something like fatigue calculations or accelerometer or accelerated testing data, and then put that into a simple report that's easy to understand and easy to read. And all of this is going to be done in an environment that is easy to use. It's very graphical in nature, so you're going to see a lot of drag and drop functionality. The second product is DesignLife, and that one is actually in the same application as GlyphWorks. So you're going to be able to share a lot of the tools and functionality. However, DesignLife is geared more towards taking FE models and processing those to do predictive fatigue calculations. So again, same environment, same graphical interface, same easy to use features like drag and drop and cut, copy, and paste. The last one is going to be automation, and this is a tool that goes along with GlyphWorks. It's going to allow you to process measured data, but in a more automated fashion. So you're going to be able to handle larger amounts of data, larger data sets, and it also helps to enable collaboration with colleagues and adds a lot of capability in terms of searching, querying, and then creating reports through automation. So let's go ahead and take a look at the agenda for today. And what I'd like to start off with is just answering the question for you guys, what is fatigue? So we can get a really good idea of that. And then we're going to jump into the 3 general methods, commonly accepted methods for doing fatigue calculations. Those are stress life, strain life, and then crack growth. I've got a couple of slides for you on talking about the inputs required for those different fatigue methods and how we actually do the calculations. And then a slide on all of the glyphs within the nCode application that have to do with fatigue, and then we'll wrap that up with a demonstration. So what is fatigue? Fatigue is a failure that occurs under repeated loading. This loading could be variable in amplitude. It could also be constant amplitude. And these loads might produce stresses that are well below the yield stress of a material, or even also the UTS of a material. So it's not necessarily a failure that occurs immediately. It's something that will occur over time, so it's a progressive failure. There are 2 modes to fatigue, or 2 different stages. The first stage is the initiation phase, where we would use a method like stress life or strain life, and that is followed up with crack growth, which is the second stage of fatigue. And in that case, we're going to use the crack growth method. The cracks themselves can grow from pre-existing defects. This could be things like porosity or inclusions in the material. And given the right set of conditions, sufficient loading, sufficient time, those cracks can reach a critical size where we ultimately have something called fast fracture. Let's continue on. So if we take a look at just the crack initiation phase, as I mentioned a moment ago, these cracks usually initiate on some type of a defect. They're going to be microscopic in scale. And on that microscopic scale, what happens is the defects will create slip bands. And these slip bands are going to be along a maximum shear plane. So you can see over on the right, these shear planes are going to be at a 45-degree angle to the alternating stress. And you can kind of think of that material as behaving like a shifting deck of cards. Again, these are going to be microscopic in scale, so we're talking about smaller than the grain sizes in the material. And Given sufficient growth or sufficient time, these can begin to grow into the second stage of fatigue, which is crack growth. At this point, the cracks are going to become physically large compared to the microstructure of the material. This is going to cause an interruption in the flow of stress in your part, and you develop very high stress levels at the tip of the crack. If you look at the diagram to the right, what you can see in stage A right here, we've got a crack that has begun to grow. It has beach marks, or some people call them striations, that have already occurred, and those occur with each cycle. And as we go from point A, which is a low stress value, and begin to increase the tensile stress, you can see that we're beginning to pull this crack apart. And that's what's happening in stage B. At stage C, we get to the maximum tensile stress in that particular cycle. The crack has opened all the way up, and then we begin to decrease the stress. So we're going down this stress cycle. That crack is beginning to close, and as it closes at point E, you'll notice what has occurred is we have now increased the length of that crack by delta A. So that is how a crack grows, and as you can imagine, if that stress cycle were larger, the delta A would in fact be larger as well. Now there's a couple of philosophies in terms of how you actually design for fatigue. We're going to talk about that. They deal both with crack initiation and crack growth, but you could actually consider the total life of a part, assuming that you're taking it all the way to failure, to be the summation of life in crack initiation and then the crack growth phase. So summing those two together is going to give you total life. And let's go ahead and take a look at a couple of different philosophies. Now, these are just some general comments, but typically what we see is that when referring to ground vehicles, we have a considerable amount of time being spent to initiate a crack. And you can kind of see that in the diagram below. We have a scale here going from left to right in terms of time to failure. Keep in mind that this is just a normalized time to failure. And for ground vehicles, the bulk of that time is just spent initiating the crack. The reason why parts are often designed like this in ground vehicles is because regular inspections are not very practical. We certainly don't take our vehicles in to be serviced and inspect for fatigue cracks. And also, the components tend to be made out of materials that are more rigid. They don't necessarily have the same type of fracture toughness that a component would have if it was actually designed to tolerate some crack growth. On the other side, we have aerospace, and this is an industry that does, in some cases, design for crack growth. So what they will do in these cases is use materials that have good fracture toughness. That's going to help them develop a structure that has predictable crack growth. They are going to design these components so that the growth rate is slow and predictable. That's going to allow technicians to catch a crack before it reaches a critical size. And then they also have the assumption that cracks are always going to be present, and therefore they do perform regular inspections. I should also notice that for the aerospace industry, when they are allowing for crack growth, they are also designing into their structures redundant load paths, so that if a crack were to reach a critical size and you had a failure, it's not going to be a catastrophic failure, and you'll be able to carry the load through adjacent components. So that brings us to the three main methods, and they are listed here. So the first two, stress life and strain life, those are both going to be used to predict and model the crack initiation. The first one, stress life, is one that makes the assumption that stress actually drives the crack initiation, and it is, historically speaking, the one that was first developed. It is one that works extremely well for high cycle fatigue. The second one, a bit newer, historically speaking, is strain life, and that is one that makes the assumption that strain is what drives the crack initiation. And as we get a little bit into the details of strain life, we're going to see that because we are basing it off of strain, we can actually begin to model plasticity. Therefore, we can see what's happening in low cycle fatigue, where our part may actually begin to yield, but not necessarily rupture due to exceeding the UTS. And then lastly, the third method on this slide right here, which begins to model how we do crack growth, is crack growth. And what it will do is come up with a stress intensity factor, and that's going to be used to drive cracks. And obviously, we're going to assume the existence of a crack or a flaw that we would specify the size of. And while we're on this slide, we might as well go ahead and take a look at the image on the right. And what this is showing us is actually a cross-section right through where a very common test specimen has failed. And what you can see, this is actually a specimen, if you haven't seen these before, is a necked cylindrical test specimen. Fairly small in size. It has a crack initiation that's occurred at the top, and once that crack initiation gets to a sufficient size, we then go into the crack growth stage, and that is what creates all of these concentric rings. And if it's showing up well on your computer screens, you'll be able to see these striations or beach marks until we get to about a third of the way through the material. And at that point, the light gray kind of transitions abruptly into this darker gray, and that darker gray is the area where we actually have fast fracture occur. So that is the point where the remainder of the part broke through in one single cycle. So let's talk a little bit about the general process that we use for doing fatigue calculations. And this process is going to be true whether you're doing strain life or stress life or crack growth. It's true also whether you're doing this by hand on a piece of paper or if you're using software like nCode to do fatigue calculations. So the first thing you're going to need are some inputs. These three inputs are going to be the geometry, your loading environment, and the material properties. All of those are going to be combined in the middle where we do our fatigue analysis, and this is where we can do stress life, strain life, or crack growth. And then ultimately, we're going to be generating some results from that. So within nCode, some forms of results might be a damage plot. If we're doing a DesignLife process, we may have some histograms or some XY displays if this is based off of measured strain gauge data. And we might also have some of our results summarized in the table. All of that, hopefully, if we're doing this correctly, going back to our inputs, where we may make changes to the geometry or the material properties to further optimize our design. So let's talk a little bit about stress life. As I said earlier, historically speaking, this is the one that came about first. It was first published back in the 1860s by August Böhler. And in fact, what he came up with was not exactly stress life, it was actually load life. So at the time, what he was doing is testing full-scale components to failure and coming up with a load versus cycle plot. That is the plot that we can see right here. And he would then use those test results to calculate life under a given load. Now, the one problem with this particular approach was if they made design changes to the component that he had characterized, let's say they had changed some geometry on it, they're going to have to repeat the characterization of the new components. So they're probably going to have to go through a lot of test specimens to fully characterize that. 50 years later, Baskin actually proposed a log-log relationship, which was stress-based, and that is what we know today as a stress-life relationship or stress-life curve. And in those cases, what we've done is we've related stress to the number of cycles to failure, and that way we can, with correction factors or perhaps FE models, we can now do calculations and know that stress on a test specimen can be related to stresses seen on a real component that we're designing. The way in which we characterize the material is fairly straightforward. We're going to break multiple specimens. That's usually somewhere on the order of about a dozen specimens. The tests done in the lab are going to be conducted under constant amplitude. So you could imagine we're going to pick a few test specimens at a given stress amplitude, test them to failure. We'll test a few others at a different stress amplitude, and then maybe we'll test a few out towards the higher cycle region. And that's going to give us a cloud of data points, which we can ultimately put a regression line through. So we're going to plot all these data points on a stress-life curve. This particular stress-life curve looks like it's in terms of amplitude, but in some cases you may also see the vertical axis is going to be explained in terms of range as well. So we'll put a regression line through it, and the key coefficients that we are looking for on this regression line are going to be the intercept and also the number or the slope, so that we can then define a line going through those data points. On to strain life. So slightly different. With stress life, what we did is we made the assumption that stress describes how we're going to model our fatigue analysis and the crack initiation. Stress actually will describe to us how hard a crack or defect is being pushed or pulled apart. Strain, however, is going to allow us to describe how much the crack will deflect. So we're going to be controlling it on strain. And if you think about the way in which the crack initiation occurs, being on the microscopic scale and dealing with deformations, strain really is going to be the key fatigue driver. The reason why early on we were able to get away with doing stress life for high cycle fatigue is because we know that stress and strain are linearly related when we are below the yield strength. And that would definitely put us into the high cycle realm. So everything works fairly well so long as we've got this nice linear relationship between stress and strain. However, if we exceed the yield point, we get into an area where we have a nonlinear relationship between stress and strain, and this is exactly why stress life does not work very well when we do low cycle fatigue. So in those cases, we're going to need something like strain life. And characterization of strain life is conducted in a laboratory setting in a similar manner to stress life. However, what we will do when conducting the test is we will actually do a strain control test. There's going to be something like a clip gauge on the test specimen, and it's going to be cycled with a servo hydraulic test machine. These specimens are going to be strained, cyclically strained between strain limits until the load begins to drop, and at that point we make the assumption that a failure had occurred. These specimens, just like with stress life, are of high quality. They're going to have a polished surface finish on them so that there's good repeatability between the specimens. And what we will then do is collect data that we can plot on a strain life curve, and we will also be creating something called a cyclic stress strain curve. So let's go ahead and take a look at those. A little bit different than the stress life curve. Here we see an example of a strain life curve. And the strain life curve is actually the summation of two curves. The first curve is this black curve right here. That is our elastic lifeline. And you'll notice that the form of this equation is very similar to strain life. We have, however, used the modulus on both sides of the equation so that we can relate this in terms of strain. And we also have a second curve. That's going to be the green line right here. And that's going to allow us to describe the plastic life. So this is going to be all of the life where we are actually yielding the part. Those two terms are going to be summed together to give us total life, or total strain life, and we can see that equation right here. And the sum is going to be the red curve plotted on this plot here. We also need to know something about the cyclic stress strain curve. Since we are going to be characterizing low cycle fatigue, we need to know the relationship between stress and strain beyond the yield point as well. And what we will do as we are conducting the test is gather stress and strain results. This plot right here is showing us a stress strain curve. The data points beginning just beyond the yield point. And if we were to plot these data points on a log-log scale of stress versus plastic strain, you can see that we can now begin to characterize this with this equation right here. In this equation, what we're going to be looking for are two coefficients. They're going to be the K and the N. Those combined with coefficients from the plastic and the elastic curves on our strain life curve, plus the modulus, are going to be all of the material parameters we need to describe strain life. So there's a little bit more to strain life and also characterizing the material. There are also quite a few more coefficients. Stress life having just 2, strain life having 7. And then lastly, let's talk a little bit about crack growth. So this is going to be the second stage of fatigue. Our crack has gone beyond a grain boundary. It has gotten to a length that is large enough to see visibly, large enough for inspections. And you know, just a couple of things worth mentioning here is that most cracks, they tend to have insufficient energy to cross the grain boundaries. However, do keep in mind it just takes one big cycle to get that crack across the grain boundaries, and at that point we are at a crack growth stage. Crack growth is actually something fairly complicated when you look at the stresses that are happening around the tip of the crack. These stresses, if you think about it, as you go to the tip of the crack, the stresses will approach infinity, and it does make it difficult to characterize that accurately. So what we're going to do is actually make use of a method called linear elastic fracture mechanics, and what we will be doing is expressing the severity of the crack with the parameter K. This is what we call the stress intensity factor, and we can see an equation right here where K, the stress intensity factor, is going to be equal to the terms on the right here, where we have Y being a dimensionless factor. This is something that we use to characterize the geometry. So for different types of geometry, you may have something like a plate with a crack in the side that's going to have a particular Y value. It may be a plate with a hole in it that has a crack on either side of the hole. Lots of different types of geometries that you can choose from. They're all going to give you slightly different Y values. And then from there, we just have a stress term as well as a length term for the length of the crack as you're getting ready to cycle that. A couple things to keep in mind here. If K exceeds the critical value, we will actually have a fast fracture. That's where we're going to have a complete breakage of the part. All right, let's go over just a little bit of the inputs and what form they might take. For the geometry input on our fatigue calculations, if you guys are working with physical parts, this may be a strain gauge part. So you can see on the left right here, we've got a part with a couple of strain gauges attached to that, hooked up to data acquisition system, and then recording data as we apply loads to it. So these loads might come from real life events. Maybe we have instrumented a vehicle and taken it out on a proving ground and gotten some road load data. Perhaps this is a component that's in a laboratory, so maybe we've got some very controlled equipment that's doing some constant amplitude loading. And the other approach might be if we're doing predictive fatigue calculations. The geometry could be in the form of an FE model, where we have solved for some stresses due to a certain loading condition, and we can take that into nCode and do some post-processing on that and some predictive fatigue calculations. The loading environment can be in a number of different forms. The first one, being constant amplitude, is probably the easiest one to conceptualize. In this particular example, we have a number of cycles that all have the same exact stress amplitude. So for all of us, it's fairly trivial just to look at this if we had some numerical values on these plots to count what the stress range would be, and then the number of cycles, and then apply that to the fatigue curve of that particular material. If you take that one step further and you go to something called block loading, we might have groups of constant amplitude loads. We can see here that this is 3 different stress levels at 3 different numbers of cycles. Again, probably pretty trivial for us to count those just visually looking at this plot and come up with an idea of how many cycles at each stress level. This becomes a little more difficult to visually look at when we're dealing with something like variable amplitude loading. So this would be an example of real measured data, something real world, and we actually have some techniques for counting those cycles. And that is displayed here on this next slide. So this particular technique, the most common technique for counting cycles in fatigue, is going to be rainflow cycle counting. And essentially what we will do is, in the example over here on the right, you can see that we've got some strain data. And we've turned this strain history on its 90 degrees so that the time scale is going down. And you can see that we have labeled each of the turning points, which are the critical points that we need to find in the data, with a letter. And what we've then done is we've projected those strains down onto a plot below, which is showing us stress versus strain. So if you think about it, if we have at point A a fairly low strain level, it could be tensile, we can plot that here, where we also have the corresponding stress with that. So here's stress magnitude, and then here's strain on the horizontal. As we begin to increase our strain, we can go up to B, and in this case that does go through the yield point. So we have gotten into the region where we have a nonlinear relationship between stress and strain. But at B, we then drop the level again to C. So that drops and creates a small cycle right here. So BCB is going to be a small cycle. And from C, we then continue onward up to point D. At D, we drop down to E right here, where we have yet another small cycle up here. So from going from E to F, this is going to create a smaller cycle, big enough, though, that we get into some yielding right here. And then we drop down to G and up to H. That, again, creates a small cycle, and then we complete with finishing up on A. So in this particular time series data, with our rainflow cycle counting, we've counted two small cycles, that's BCB, GHG, one intermediate cycle, that's EFE, and then one very large cycle, it's going to be ADA. So that's basically how rainflow works, and we can actually display this in a nice manner on a histogram display where we can show range versus mean. And this sample right here is a pretty typical distribution of cycles that we may see, where we have a lot of cycles down near a range of 0, meaning we've got a lot of really small cycles. It's very likely that they don't contribute to damage because they are so small. And then as we get out to the very largest range, this is going to be showing just the few biggest cycles that we have in our time series data. And it is likely that these large cycles, if they do produce damage, are the ones that will contribute to almost all of the damage. And we'll actually see that in a demonstration in a little bit. All right, so we need to come up with a way to accumulate the damage. And the best way to describe this is just to take that block cycle loading example that we saw a few slides ago. In this case, we've got 3 different strain levels that have 3 different numbers of cycles associated with each of those blocks. And we're going to make use of a rule called Miner's rule. So we have an equation here where we're going to sum the ratio of little n over big N. And we are going to be summing that up, and anything that is less than 1 means that we actually have life left in a part. If we equal 1, the classical definition of that is we have initiated a crack, so we have a fatigue failure that has occurred. Now the way this is going to work, we have this first block, strain 1, that's going to be at this particular level right here. We have a certain number of cycles that have been counted. So that is going to be little n. And little n is going to go along this horizontal line. And in this particular example, we can make the assumption that it doesn't quite get to the fatigue curve. So if we said that it got a third of the way, that would be little n over big N would be 0.33. If we said the same thing was true for strain 2, the smaller cycles right here, if we got a third of the way as well, and then one more time if we got a third of the way on the largest strain amplitude, that would be up here. Sum all those together, we have a value of 1 that would give us a fatigue failure. So it's really just going to be a function of the ratio of how far we've gone along this horizontal line to how many cycles that part could actually tolerate at that given strain level. This particular approach applies to both stress life and strain life, and that is the exact approach that would be used in many of the fatigue calculation tools inside of nCode. The material properties here you can see on the far left we've got multiple fatigue curves. These are just fatigue curves, stress life based of different alloys of aluminum. We have strain life curves right here. They have this inflection point where you can see the transition between low cycle and high cycle. Again, this is of multiple fatigue curves. But keep in mind, strain life also needs to know the relationship between stress and strain in the nonlinear region as well. So we're going to have that information available to us. And then lastly, we also have material properties for crack growth. And in this case, this is the delta K effective plot, which would be used for crack growth. As far as the tools inside of nCode are concerned, here is a list of most of the glyphs that would perform fatigue calculations, and I've divided them into different regions. If you guys are working mostly with test data, meaning you're going to be doing fatigue calculations using GlyphWorks, and you're doing strain life or stress life, you have 3 different glyphs that you can make use of. The first one right here is going to do actual stress life calculations for you. The other 2 are going to be relative life calculations. They will be stress-based though. We have a strain life glyph as well in GlyphWorks, and we have a crack growth glyph here. On the design life side of things, we have quite a few different stress life glyphs. The basic one is this SNCAE fatigue. The other ones, for example, the spot weld and the seam weld, those are stress-based, but they are specifically designed to deal with FE models that have been built to represent spot welds and also seam welds. We have a vibration CAE fatigue glyph. That one is also stress-based, but instead of giving that glyph data in terms of time series data, we would be giving it data in the frequency domain. It could be a PSD or a swept sign. And we also have some newer tools as well available in nCode 8, short fiber composites, and also the ability to do adhesive bonds. We have a strain life glyph as well, and we also have a crack growth glyph on the design life side too. So at this point, what I'd like to do is share nCode with you, and I will do a demonstration so you guys can see the environment. So hopefully everybody can see the environment for nCode. For those of you who are new to the application, I want to just point out a couple of key areas. The first one is this area called available data. This is going to show us all of the recognized file types from the directory that I had just chosen to work out of. So I've just pointed nCode to a directory, and it's going to organize for me all the different file types. You can see it has organized those. We've got some Excel spreadsheets. We've got some FE models. There are a number of different FE softwares that we can read from. And we've also got some examples here, some time series data. In the middle, we've got our workspace, this gray graph paper area. That is where we're going to be dragging our available data out, and we'll also be assembling additional glyphs, which will come from these glyph palettes over on the right. These glyph palettes each having a number of glyphs within them as well. Another area that's probably important to mention is this menu all the way over on the left. It's called Manuals. A very, very good resource for documentation and for help. And if I make this a little bit wider, you'll be able to see. We have a number of PDF documents here that have work examples. There are over 24 work examples for GlyphWorks. There's somewhere on the order of 15 work examples for DesignLife. Each of those work examples are going to have step-by-step instructions on how to do a particular type of calculation, and they also will come with all of the necessary files to do those work examples. So what I'm going to do for you first is some fatigue calculations on strain gauge data. So this is more GlyphWorks related. And the first thing I'm going to do is drag some time series data out. And I'm going to go ahead and enlarge this glyph just by clicking here. And I also know that this time series data has 5 channels, so I'm going to show all 5 of those. So here we have strain gauge data measured for about 580 seconds. And what I'm going to do is bring a couple of other glyphs out onto the workspace, and we're going to assemble a process. So I'm going to go to the fatigue glyph palette here. I'm going to grab the DesignLife glyph and attach it to this blue square on the right-hand edge of my time series input glyph. These squares are called pads. We've got inputs on the right-hand edge. We've got, outputs on the right-hand edge, inputs on the left-hand edge. These pads are color-coded. They will signify the type of data that's going through them. So blue is going to be time series data. Green is going to be either metadata in this example, or what we'll see later is going to be FE results. Red is going to be histogram data, and then this orange color is going to be multi-column data. The next thing I'm going to do is drag some display glyphs out onto my workspace. And the first one I can do is grab an XY display here. And that's going to be, if I mouse over these, you can actually see some text that describes the type of information that will be coming out. So this is going to be damage displayed in the time domain. We're going to grab a histogram display, and we're going to attach that to the damage histogram. And I'm also going to create a second pipe to this display glyph that's going to show us our rain flow. And then 2 more glyphs right here. We're going to grab a metadata display that's just going to allow us to display some summary results. And then the last thing is going to be a data value display. So this is just a table that's going to show us our cycle list. We can drag that down here. And what you can see now is I've assembled all of the glyphs that I need. The last thing I need to do is finish off the inputs. As you can see, the loading environment has been captured with the actual measured strain histories. We need to take a look at the material and also the geometry as well. For measured test data, our geometry can be controlled in part with KF. So we have a fatigue concentration factor that we can manipulate. By default, it has a value of 1, and also we can define the material properties. nCode comes with several material databases, and I'm just going to make use of a material in one of those. And it's going to allow me to go to this material tab, and I can grab this aluminum alloy, for example. So at this point, I can click the OK button, and I can hit this blue triangle. That's going to run the process for me, and now I have fatigue results in all of my display glyphs. So let's go ahead and go through those one by one. We'll expand this first one, and we can show all 5 channels. In this particular example, you can see that the first 2 channels have small spikes in them. These spikes are damage results. If, for example, on channel 1 we had a fatigue failure, the sum of all these spikes would equal 1. That is according to Miner's rule. On the last 3 channels, we actually have a straight line going across at 0. So what we can see here is that the strain cycles were not big enough to produce any damage. Therefore, we have 0 damage on those channels. We can display this also on histograms, and what you can see here, the lower histogram is showing us our rainflow cycle counting. So again, lots of cycles that are fairly low in magnitude. If we go all the way out here, we have just a couple of cycles that are large, and this one single cycle out here is in fact the one that contributes to most of the damage. Damage histogram being displayed in this plot above. So here is a very large red column that is creating most of the damage, and then we have some damage being created by these cycles that have, let's call it an intermediate value in terms of range. We can cycle through these, so this is just for the first channel. Here's the second channel, and the last 3 channels are going to have 0 columns in this damage plot in the upper part because those cycles were not large enough. All right, and then lastly, we can look at the metadata. There's lots of ways in which this display can be manipulated. We can create a table if we'd like, but if we just drill down the branches here, we can see we have some DesignLife results for channel 90, and if I were to expand that, you can see that we have damage being displayed in a number of ways. We've got damage displayed per hour. There's lots of our customers that like to report damage in terms of hours. We can also display total damage, and that would be for the total duration of the time series data. So that was the 580 some seconds. Or if you prefer, we can also display it in terms of life. And this type of information is going to be available for all of the other channels as well. And lastly, what we can do is expand this data value display here. And this is just showing us the cycle list. So this is cycle by cycle, what was counted when we did the rainfall cycle counting. And if we look down at the bottom here, we can see this is for channel 90. That was that first channel. And with this blue arrow, we can cycle through all 5 of those channels in the time series data. All right, so that was a very quick, very basic example of doing fatigue calculations on real measured strain gauge data. The next thing that I'd like to do is just show you how you can do some fatigue calculations on an FE model. So I'm going to clear this out. And in this example, what I'll do is grab an FE model. Let me go ahead and display this for you guys. So very simple structure right here. We've got a cylinder that we have performed simulations on in FE. In this case, it came from Abacus. And this example actually has 2 load cases. I'm really only going to make use of one of them in this demonstration. We could do 2, but just for simplicity, we'll make use of one. And what we're looking at right now are the stress results from FE. So we're going to make use of these stress results. And that can be done by grabbing a fatigue calculation glyph. In this case, I'm going to grab the DesignLife fatigue calculation glyph. And we need to define the 2 remaining inputs for doing our fatigue process. That's going to be defining the material and our loading environment. So our material, we're just going to right-click and select Edit Material Mapping. And much like before, what we're going to do is just grab a material from one of the databases and just drop it up onto our FE model. This FE model, like I said, is fairly simple. It only contains 1 element set. You may have an FE model that's representing an assembly of lots of different parts. They may be made of different materials. You can have all of those displayed here, all those property sets, and you can assign, just with a drag and drop, unique materials to each of those element sets. So a lot of capability there. And we'll go ahead and hit the OK button. Now I need to define the loading. And what I'd like to do is just define a very simple loading. This is going to be constant amplitude, and what we'll do is just the first load case. That's going to be this bending load case, and I know that the FE model was sold with a unit load, so they had applied a load of 1 Newton to produce the stresses that we can see that we're going to post-process, and I know that that is too small if we were to cycle it back and forth from 1 Newton to -1 Newton. So what I'd like to actually do is scale it up. I'm going to cycle my part from 13 newtons to -13 newtons. That's going to define my constant amplitude load cycle. And we'll drag out a couple more glyphs. We can drag out an FE display glyph. It's going to allow us to see things graphically. And then also a data value display that's going to allow us to see a table. And at this point, we're ready to run our process. We've got all of our inputs. Geometry, material, and loading. We've got our DesignLife calculation glyph and then some display glyphs to see the results. We'll click the Run button here. And now if we were to enlarge our FE display, we can see that we have no longer a plot of stresses, but a plot of damage right here. So this is, imagine bending this shaft back and forth with a load of 13 newtons and then back to -13 newtons. And we have damage results. We can flip this around if you prefer to look at this in terms of life. We can do that as well. And now if you look over at the legend, what you can see is that the minimum value is 1,163. So what that's suggesting is in these critical areas, right where we have these darker reds, we could repeat that constant amplitude load of 13 newtons to negative 13 newtons a little over 1,000 times before we can expect a fatigue failure to occur here. And keep in mind that fatigue failure is going to be a crack initiation. All of that information can also be displayed in a table, and that's just right here. So here we have results, each row being nodal results, and then the different columns are different fatigue results that we've calculated. The key ones here, the ones we've seen graphically already, are going to be column 6, that's damage, and also column 10, that's going to be life. So that actually concludes my demonstration, and what I'd like to do now is just go back to the PowerPoint, wrap up with the last couple of slides, and open it up to questions. So just to kind of review the agenda that we had for today, fatigue, as we learned in the very beginning, is a progressive failure that happens over time with cycles of stress or strain. These do not necessarily have to exceed the yield stress of a material before fatigue failure occur. We've got a number of ways in which we can do the analysis. For crack initiation, we've got stress and strain life. For crack growth, we have the crack growth technique. And we have lots of tools within nCode that would allow us to do those fatigue calculations. So with that, I would just like to thank you for your